Hello friends, today I'm going to solve LeetCode problem number 863, all nodes distance k in binary tree. So we are given the root of a binary tree, the value of the target node, and an integer k. And we need to return an array of values of all the nodes that have a distance k from the target node. And we could return our answer in any order. Okay, so now let's look at this example here. So we are given the root starts from 3, and this is how the tree looks like for this given tree, binary tree. And then we have the target 5. Okay, so our target here is 5, which is this node here, and the integer value k, which is equals to 2, which means that we need to find all the nodes which are at distance 2 from 5 in this binary tree, and then return those nodes in an array, and we could return them in any order. So let's see. So we start from 5, we can move to all of its branches. Okay, so let's move to 3. So we moved one distance, right? And now we again move one more distance. Now the total distance here is equals to 2, and we have a node which value is 1, so we add this node to our resulting array, which is 1. Here we have it. Next, similarly, we move to 6. From 6 we do not have anywhere to go, right? So we just stop right there from 5. Now we need to go to 2, and from 2 we have two ways. So from 2 we go to 7. Now 7 is at distance 2 from 5, so we add 7 to our resulting array. And also from 2 we have a node 4, which is also to distance from 5, so we add the node value 4 here. So we have in our array 7, 4 and 1, and this is our result. So basically this is what the problem statement is. Now let's look at the constraint. The number of nodes in the tree are from 1 to 500. Okay, and then the values could be from 0 to 500. All right, and all the node values are unique, and target is the value of one of the nodes in the tree, and k is from 0 to 1000. Okay, so since we are given that all the nodes are unique, which means that there will only be one node with the value 5. We will not have another node with a value 5. For example, if this 0 was a 5, then how would we solve this? Basically that would mean that 5 from here, 2 distance would be this one, and for this also we need to count for 2 distances for, and that would result in some some ambiguous answers or something else. So since all of them are unique, so this makes our problem more easier. So now let's look at this in more detailed way, and how we could actually solve this problem. So I'm just going to copy this figure and paste it over here. Okay, it's a huge figure. All right, now let's look at this one. So here we are given a tree, right? This is a tree right now. This is a tree, which means that we can only move from a root node to its left child and to its right child. Let's see what we are doing here. We have the node 5, which is the target node, and from 5 we are moving to its root left child and right child, which is fine. Again from 2 we are going to its left and right, which is again fine. But what in this case, from 5 we are going to 3, and 3 is what? 3 is the parent of this node, right? And we do not have any pointer to the parent. If you look at the function definition here, we have that the node has its left and its right, pointing to left and right, but it doesn't have a parent. So that is what we need. In this case, we need to access its parent so that we can get our result, which is equals to 1, right? So how are we going to do that? Either we can add pointers from all the nodes to its parent, or we could create a graph. So here I'm just going to create a graph. So what happens in graph is since this is a binary tree, we can only move from parent to its children, right, in this way. So but in case of graph, we will not have any uh, like we will not have any kind of direction. We can move in any direction. We can move from 5 to 3 and from 3 to 5 and anyways, right? So that is what we are going to do. We are going to create a graph. Okay, so for graph, how are we going to do that? We need to find all the nodes connected to the given node. So for 3, what do we have? For 3, we have the nodes which are connected are node with value 5 and 1, right? And what about 5? For 5, we have the nodes which are connected equals to 3, 6 and 2. So these are the nodes connected to 5. Similarly for 6, what do we have? We have only 5. So in this way, we are going to create an array of all the nodes that are connected to the given node. So from 2, we have 5, 7, 4. So in this way, we are going to create the graph. And if you would see, a node will have maximum of three elements. That is 3 nodes that it is connected to. Because in binary tree, we have a parent nodes to its child, and child can have maximum of 2 children, right? So it can have maximum of 2 children and 1 parent, so that will only result in maximum of 3, but we don't need to consider that here. Now after we have created our graph, what we'll do is we'll start from our target node. So from our target node, which is 5, we will now move across all of these nodes. So from 5, we can go to 3, to 6 and to 2, right? So we can go in these 3 directions. So these will be all at length 1, right? At length 1. Now for 3, where can we go? From 3, we can go to 5 and 1, right? From 3, we can go back to 5 and to 1, but we don't want to go back because we have already been there. And actually, that's our target. So we want to go further away so that we can find our target. So from 3, we actually go to 1, okay? So this is 1, and now here we have found our result, which is at distance 2. So we add 1 to our resulting array. Similarly, from 6, we can go to 5, right? But we don't want to go back. So we will, in order to know that we have already traversed that node, we are just going to create a new array, a new set of visited nodes. Okay, so this is a visited nodes. This is our resulting array. All right, and visited set of visited nodes, and we have already visited 5. Now since we have already visited 5, we are not going to visit 8. So from 6, we are not going anywhere. Now what about 2? We have traversed 3, 6, and what about 2? Now from 2, we have connections to 5, 7 and 4. 5 we have already visited, so we are not going to visit it. Now what about 7? We can visit 7, right? So 7, when we visit 7, we know that it's at distance 2 again. So 7 comes in our resulting array. And similar is with 4. 4 is also our result. So we add 4 to our resulting array, and that's our result. Okay, and while we are adding these nodes, we need to also add them to our visited nodes. So since we first visited 3, so we are going to add 3. We also visited 6, so we are going to add 6. We also visited 2, so we add 2. So that if it is a long graph and we have a value of k greater than that, then we don't visit these nodes. Okay, so basically this is the concept that we are going to follow to write our code. So now I hope you understood the concept. Let's now dive into our code. Okay, so what do we need? We need to first create a graph, right? Since we created the graph first, so we need to first create the graph. Now how can we create the graph? For a graph, we can either use map, like here 3 has an array. Okay, so basically we are pointing this node 3 with all the nodes that are connected to this. So we can either create an array with index from ranging from 0 to 500, because we can have the values of nodes only from 0 to 500, right? So those index would be actually the value of node, and the array at that index would carry these elements, these arrays. So we can either create an array or we can create a map. Here I'm going to create an array. So let's create an array, calls new array of length 501, because our value ranges from 0 to 500, and those are total of 501 number, right? And since each of the array is of each of the element in this array is also an array, so we are just going to do that here. Each element has new array. Okay, now it is an empty array of length 501 with each element also being an array. Now what we did is we created an array. For example, we create an array of arrays, and each of the array here is empty. So we created this. Now we are going to fill this with the values. So at index 2, let's see index 2. At index 2 we are going to have this array, so index 2 will have these values, and so on. So for that, now what we're going to do is we are going to iterate traverse across this tree and add these elements into our graph. Okay, so for that I'm going to perform a depth first search. So function as, and we need to pass a node to our DFS, right? Now what are we going to do is we are going to check if, okay, let's first check get left equals to node, the left of the node, and let right equals to the right of the node. Also we need to check if the node is empty. If the node is null, then we cannot get the left and right, right? So if the node is null, then we just return. Okay, in the end I'm going to modify this algorithm a little, but for now just like I'm following the process that I used to while I was solving this problem for the first time. So this was how I was solving it. Now if we have the left node, that is we have the left node, so for the at this array at the index of this node, so array, okay, array at index node value, we are going to push what, the value at left, right? So what I did is, let's suppose we are starting at this node and we are checking here if it has its left node or not. Since it has its left node, so we are adding to our array at index equals to the value of the node, that is at index 3 of the array we are pushing 5. So at index 3 we'll have the array with element 5. Okay, we are also going to do that the same for the left node as well, because left is also connected, this node is also connected with 3, right? So we have to do it the reverse way also. So node val and then DFS to the left. Okay, similarly we are going to do it for the right side and change it to right. Okay, now here one thing, we are checking here if the node is null or not, right? But since we are already checking if the null is, if the left is not null, that is only when we are calling our DFS, right? Here also we are only calling DFS when the node is not null, so we do not actually need this. We only need this to check if the root is not null. So if the root is not null at the end, when we call our DFS, we are calling it using our root, right? So since if the root is not null, then we are going to call our DFS function. If the root is null, then we just return an empty array. Okay, so this is how our DFS function looks like. Now this will create our graph. CREAT. Okay, I'm just bad with the spellings. Graph from the tree. Alright, so we have our graph now. Now that we have our graph, what did we do with the graph? We started traversing from the target node, right? We start traversing from the target node and we keep track of our visited node as well. So let us create a visited set equals to a new set. And one thing here, while we are traversing, we are starting from our target node and we are traversing in a DFS order. If you noticed, we traversed from 5 to 3, 6, 2, and from 3 we are traversing to the to its connected nodes. So basically we are performing DFS. So for DFS we need a queue. So I'm going to create a queue here, and initially the queue will have the target value, okay, which is this target, and target is a node, so we need the value of the node, so that's why I'm using the value here. Now that we have our target node, let's start our iteration. So we are going to iterate q u e u e q, as long as the length is not equals to 0 and as long as k is not equals to 0, right? So as long as we have length greater than 0 and k greater than 0, we are going to iterate over here. Now here we are going to create a new array. This is basically a queue where we are going to store all its children. So from 5 we have connections to 3 to 6, right? So this will be stored in this array here. So we are going to do it as long as the queue is not equals to 0. Now we shift, let our new target is q dot shift, so we get the first element from our array, from our queue, which is now here equals to 5, okay, because we have the target value in the queue, so that will be equals to 5 here. And 5 now we are going to iterate I equals to 0, I is less than the graph, right? The graph we created, we are going to iterate over each of these nodes, right? So that is what we are going to do from our array dot array at index 5, not 5, we at target dot length and I plus plus. So for this, and we are going to iterate, and we are also going to check if the array at target at index I is equals if it is present in the set. So set, I mean visited, has this array, this element, then we are just going to continue, else, okay, as I visited, else what we do, we are going to add to our children array children dot push, we are going to push array target index I, okay. So this is what we are doing here, and then once all of the elements are pushed from that given level, okay, so what we do here is we decrease the value of k, and then also we need here we need to add these two are visited, so add the target to visited, right? Because we have an empty set here, and once we take the target value, which is 5, we need to add it to the visited, because now we are visiting 5, and from 5 we are adding its children. Its children are 3, 6 and 2. And now once we have added its children, we have reached the next level, right? So that is why we are decreasing the value of k. And then to q, we are now going to push the children. So here I'm doing array destructuring, and then okay, so once that's done, in the next iteration, now what happens is in our queue we'll have the values 3, 6 and 2, and our children will again be empty, and our k value of k is reduced by 1, right? So now it's equals to 1. And now while all the length of queue, that is while the queue has the elements 3, 6 and 2, we are going to perform this thing again. So what we are doing here is now we are shifting. So if we have the first element, which is equals to 3, then the target will be equals to 3, and that's added to our visited set. So now our visited set will have 5 and 3 both, and okay, and then for 3 we are now going to iterate over all of its connected node. So the nodes connected to 3 are 5 and 1. Since 5 is already visited, we do not add it, and 1 is not visited, so we add 1 to our children. So now our children will have 1, and then in the next while loop, now we iterate over the next element, which is equals to 6. So for 6, again what we do is we add it to our visited node. So we add 6 to our visited node, and then for 6 we are going to iterate over all of its connected nodes in the graph, right? So the nodes that are connected is 5, and 5 we have already visited, right? And it doesn't have any other nodes, so we are not going to add anything to our children array. And then next what we are going to do, we have the node 2. So for 2 now we do the same thing, we shift the value 2, and then we add 2 to our target. So here we have 2, and then we iterate over all the connected nodes with 2 in the graph. So we have 5, and 5 is already visited one, so we do not add it. We have 7 and we have 4, and these are not visited nodes, so we add all of these nodes to our children. So what do we get is 7 and 4, right? Now that we have added to our children, and in the next iteration we have our queue is also empty because we have traversed over all of these elements, right? So here what we do is we decrement the value of k. The k was equals to 1, now k is equals to 0. That is, we have traversed the length 2, right, for these nodes. Since we have traversed length 2, and here I am pushing all the values of children to our queue, and then in that case our queue will have these values, right? Because our queue now here is empty, so our queue will now have these values. And in the next iteration we see that the length of queue is not empty, however k is equals to 0, so we'll break out of this loop. So our result is actually stored in the queue itself. So what we are going to do is finally we are going to return the queue. Okay, so this is what our answer should be. Let's try to run our code now. Awesome. So our test cases have all passed. Let's look at the submission. Awesome. So let's look at the time complexity and space complexity. First, talking about space complexity, we are using an array, but the length of the array is fixed, right? And also each element in the array will only have maximum of 3 elements, so that is also fixed. So fixed means that it's not going to increase, right? So that would be a constant space complexity. And here we are performing a DFS function, right? DFS over each of the node. And since we are iterating over each of the node, it in the tree, so our time complexity would here depend on the number of nodes in the tree, so that would be O of n. Also the space complexity will be O of n because we are using stack here. All right, so that is our time and space complexity for this one. Let's look at our visited set. So visited set will also have maximum of n number of elements, okay, and the queue also n number of elements. So our space complexity is O of n, and time complexity here also becomes O of n, because even though we have this while loop here, it doesn't affect the outer while loop. Okay, so that is what our time complexity and space complexity is. Hope you enjoyed my solution. Let me know in the comments down below. Thank you.